Okay, we're going to start talking about solutions, which in your textbook is chapter 11. So I'm going to share Annie with you. This is Annie who's giving the lecture with me today. So let's see. Oops, she stepped on something. Okay. So solutions and their properties. We've been essentially using solutions and that concept as we went through equilibrium kinetics, but it seemed more reasonable to talk about them officially after we did our thermodynamics. Some of you haven't talked about delta G's or Gibbs free energy and spontaneity in Chem 107 if you used OpenStack, so just makes more sense to do this topic after that. So a solution is a homogeneous mixture. The solvent is the major component, the solute's the minor component. So you can have all types of solutions, gas and gas, gas and liquid. So this is just a table. In general, we talked a lot about liquid in liquid and solid in liquid when we were talking about acids and bases. So when something goes into solution, you have to think about a couple things. So will something dissolve? So will it be a spontaneous process, for example, to dissolve sodium chloride in water or gasoline in water? And we know that sodium chloride, yes, it's spontaneous. Gasoline, no, it's not. So we have to talk about the whole delta G function because that tells us if something's spontaneous. So the first part is just the energy changes, which would be the delta H change. So when you go from pure solvent on the left and pure solute on the right and mix them into a solution, you have to break the solvent-solvent interactions and the solute-solute interactions, and then you'll make these new interactions, a solute with a solvent. So if you're talking about something like sodium chloride and putting it into water, you have to break apart the ionic bonds that are holding the sodium chloride, the purple and green balls in the middle in the solid phase. And then you have to reform on the far right these interactions between the water molecules and the ions that are now going into solution. So the water molecules are going to align themselves so that the negative ends are towards the positive and cation and opposite for the anion. So there's also an entropy change. So when you think about taking the solid and the liquid on the left and making them into a solution, you're going to create more entropy because there's more randomness in the solution. So the delta S tends to be positive for a something dissolving in another substance in order to make a solution. So you can also have liquid-liquid, and that should also be true, that the two pure liquids are less random than the solution where the two types of molecules are allowed to move freely between each other. And so when we think about whether or not a process is spontaneous, it's really going to be the delta H that makes the big difference, because in general, that delta S term is positive. It's not always true, but in general, that's true. So if the process is endothermic for dissolving, then the reaction, whoops. So it doesn't necessarily mean this line does not follow this line. So it's not necessarily spontaneous if it's endothermic or exothermic. We have to look at the contribution from delta S as well. So you can have endothermic processes where things dissolve, something like ammonium nitrate that makes a good ice pack because it pulls heat out of the water. And also an exothermic one, something like the reaction between an acid and a base is exothermic. So we can decide if they're spontaneous based on our delta G function that now we know more about after we've done our chapter on thermodynamics. Oops. So just looking at this table in a little more detail. So the delta S for all of these dissolving in water is positive, so favorable. But the delta H for some are positive and some are negative. So it just depends on the relative interactions, whether or not solvent-solvent, solute-solute interactions are stronger or solute-solvent. Okay, so during the process, something like calcium chloride dissolving in water, it's exothermic, so the temperature of the water goes up. But as I mentioned, ammonium nitrate is a great substance to use as an ice pack because when it dissolves, it's endothermic process, so it pulls heat out of the water and cools down the system. And so this just depends on what I just mentioned. If the solvent-solvent interaction, that's the energy that has to be absorbed to overcome the interactions between solvent molecules, that's going to be positive. And then the solute-solute, you have to overcome those also. So if the energy has to be absorbed to overcome the intermolecular forces holding solute particles together in a crystal. But it's really the solvent-solute interactions that are important. So energy is going to be released when solvent molecules cluster around solute particles and solvate them. That's going to make it a negative delta H. So it's really the relative values of each of these. So 2 positive delta H's and a negative delta H. Your question is really going to be whether it adds up to be positive or negative. And so this is just showing you that 2 positives on the far left sometimes can come back and make the overall process negative if the solvent-solute interactions are more negative. And then on the right, you have the opposite situation where the 2 positive impacts are greater than the negative energy you get back when the solvent interacts with the solute. And so in that case, the delta H for solution is positive. You have to put energy in. So when you think about whether something dissolves, you really have to think again about, the whole process. If something's spontaneous, its delta G has to be negative. If delta S tends to be positive, that helps. But your delta H might be more positive, which would mean that delta G would end up being positive. So you have to look at both the delta H and the delta S. And from this equation, you can also see that whether or not something is soluble is going to be temperature dependent because of the T times delta S. And so now we'll just talk a little bit about concentration units. You've already talked about most of these in 107. So molarity, moles of solute over liters of solution, mole fraction, moles of component over total moles of solution, mass percent, mass of a component over the mass of solution times 100, and then molality, which is moles of solute over mass of solvent. And that last concentration unit is extremely useful because the volume of something depends on temperature. So for example, that would mean that the molarity actually changes with temperature because the volume of the solution changes, whereas molality doesn't depend on temperature. So depending on what kind of problem you're doing, you might choose a different one of these concentration units to make it a more useful way to do your calculations. So assuming that seawater is an aqueous solution of sodium chloride, what's its molarity? Tells us the density and the concentration in mass percent. So we're going to think about how do you convert from one to the other. And the easiest way for me to think about that is to think about what units do I have and what units am I going to. So if I have the mass percent, I have mass of sodium chloride over mass of solution, and I want to convert that into moles over volume of solution. So the first thing we're going to do is pick a volume. And in this case, we'll pick, rather than a volume, we'll pick a mass of the solution because we're starting with mass percent. So if we say we have 100 grams of solution, given we know the density of that solution, we can calculate the volume. So the mass of the solution times 1 over the density. So 1 milliliter is 1.025 grams. Then you'll be in milliliters, convert that to liters, and you have the volume in liters. we can take the mass. So if we have 100 grams of solution, 3.5 mass percent means we have 3.5 grams of sodium chloride. Change that into moles, and then you're ready to just finish the calculation. Now you have moles of solute and you have volume of solution in liters. So we're going to take those two numbers and just divide them. Here's another one using the units of molality. So what's the molality of a solution prepared by dissolving 0.385 grams of cholesterol and 40 grams of chloroform? So we're going to convert the mass of cholesterol to moles, because we know, and you should have these written on your note card for your test, that molality is moles of solute over kilograms of solution. So we know we need to convert the cholesterol into moles. And then we need to convert the solvent, the component in larger excess, into kilograms. So we have 40 grams of chloroform. We can convert that into kilograms. And then we take the ratio and we'll have molality, which is moles of solute over kilograms of solvent. So this is just a table of those concentration units. And it is useful to have them written down because it's super easy. I mean, you have more molarity with liters of solution, molality with kilograms of solvent. So there are subtle differences. And so it'd be wise to have these written down someplace. So some factors that affect solubility. A solution containing the maximum possible amount of dissolved solute at equilibrium is called a saturated solution. So solubility is an equilibrium process, just like the other equilibrium processes we've talked about this block. And a supersaturated solution is a solution that contains greater than the equilibrium amount. And you can create that often if solubility is temperature dependent. You can raise the temperature way up, dissolve a whole bunch, and then as you cool it off, it's above the temperature, or it has more in it than it should at those lower temperatures. But until the kinetics are right and the solute starts to precipitate out, you can have this solution that has more in it than equilibrium would suggest. This is a picture of that process. It's a nice demo where you have a supersaturated solution of sodium acetate and water. So you've heated this way up, you've made it so that as it cools off, you have more sodium acetate in the water than the cooler temperature should allow. And the second you put a little seed crystal in so that the kinetics, so that it can start to precipitate, it will all just crash out of solution and it makes this beautiful crystal. This is a graph of the concept that I mentioned earlier. Because of that T and the delta G, so delta G equals delta H minus T delta S, we know that temperature should impact the delta G, therefore should impact the solubility. So this shows you for different compounds. In general, solubility goes up with temperature. So temperature on the x-axis, solubility on the y, but not for everything. In this case, there is this one at the bottom that the solubility actually goes down. Sodium chloride, the temperature doesn't appear to impact its solubility at all. So in general, it goes up with temperature, and it makes sense it would go up with temperature because temperature, if delta S is positive, will make that component a bigger negative. But this much must imply that this cerium sulfate must have a negative delta S for dissolving in order for its solubility to decrease with temperature. Some other factors that affect solubility: if you have a solution of a gas in a liquid, then the pressure is going to affect solubility. So you have equilibrium, and if solubility of the gas is dependent on the pressure of the gas above, then the solubility is going to go up as you increase the pressure. And so the solubility is equal to K, which is a constant, and it would be different for different solutions. So you'd measure that experimentally times the pressure. So the solubility of CO2 in water is 3.2 times 10 to the minus 2 molar at 25 degrees in 1 atmosphere. What's the Henry's law constant? So we're just going to solve for that K. So here we have our solubility. If we divide it by the P, we'll get K. And so depending on what units you use for pressure and solubility. In this case, we used moles per liter in atmosphere. So our Henry's law constant will be in units of moles divided by liters times atmosphere. And it will be 3.2 times 10 to the minus 2. And so this is also looking at the fact that as temperature goes up, the solubility of gases in a liquid tend to go down. So that makes a lot of sense. They're going to prefer to be in the gas phase as the temperature goes up. So this is showing you that, and it looks pretty consistent for all 4 of these, that their solubility decreases as temperature goes up. So these are gases dissolving in water. This is a picture, I'm pretty sure it has something to do with, you can look at it in your book. I think of the solubility of nitrogen in your blood. So there are some properties that are simply properties of the number of particles you put in solution, not the type. So a colligative property is a property that depends on the amount of a dissolved solute, but not on its chemical identity. There are 4 of them that are important, and we will go through them. They're actually related to each other in a lot of ways. So the first one, vapor pressure lowering. It makes sense that if you have a solution, that the pressure above due to any component is going to depend on the concentration in the solution. So if you start out on the right, you have a pure solvent, you have a certain amount of vapor up above and you can measure the pressure. But if you add a non-volatile solute, so something that doesn't go into the vapor phase, you're going to have essentially less likelihood for the solvent to go into the vapor phase. And so the vapor pressure goes down. This is called Rayout's law, that the pressure due to a component above a solution is equal to the pressure of the pure solvent times the mole fraction of the solvent. So this says the vapor pressure of pure water at 25 degrees is 23.76 millimeters of mercury. What's the vapor pressure of a solution made with 1 mole of glucose in 15 moles of water? So glucose is not volatile, it says. So glucose will not go into the gas phase. So we need to figure out the mole fraction. So we have, let's see. Yeah, so it's the water. So you want the mole fraction of water, not the mole fraction of glucose. So you have 15 moles of water, and the total solution is a mole of glucose plus 15 moles of water, so 16 moles total. So this fraction right here is your mole fraction. Here would be the vapor pressure of pure water, and so it's slightly lower, 22.3 millimeters of mercury. So the vapor pressure lowering depends on number of particles. So you have to know how many particles you put into solution. When something, for example, like glucose dissolves, it's a molecule that stays together. It's sugar, so it doesn't separate into ions. So if you put in 1 mole of glucose, you have 1 mole of particles. But if you put in 1 mole of sodium chloride, we know it dissolves into ions, and so you'd have 2 particles. So you need to have the mole fraction of the particles when you're doing that equation. So I is called the Van Hoff factor, which takes into account that if you put a mole of sodium chloride in, you get 2 times that number of moles of particles in the solution. So why is the vapor pressure lowering? When we think about it in terms of delta G, so if delta G is more negative, the process will be more spontaneous. And so when we think about this case, vaporizing something, it's not going to be dependent on the delta H. So we're essentially saying it's independent of the type of particles. And so we're assuming that the delta H for the solvent and the solution are about the same for vaporization. So that would mean that if water is pure, takes the same amount of energy to vaporize a mole as it would if water was in a solution with sodium chloride, for example. And what that's really saying is if you have a solution and it's not very concentrated, the solvent is pretty much in the same environment, whether it has a little bit of sodium chloride in it or not. So we're assuming that the delta H vaporization for the solvent and the solution are the same, but the delta S is different. So if delta S is more positive, it's going to be more likely to vaporize. So when you think about the pure solvent, it has less entropy than the solvent when it's in a solution. And so the blue line on the left is showing you that the entropy change for the solvent going into the vapor phase is bigger than if the solution has a higher entropy. You don't gain as much to have that solvent go into the vapor phase. And so because delta S of vaporization for the pure solvent is bigger, that means the process has a bigger negative delta G for vaporization, and therefore the pure solvent is going to have a greater vapor pressure at equilibrium. Vapor pressure lowering of solutions. So this is just using Rayout's law for a two-component system where both components are volatile, both go into the vapor phase. So benzene and toluene are both volatile. So you have, for the pink line, it's toluene changing pressure above as you add more benzene to the solution. So no, pure toluene on the right-hand side, and as you add more benzene going from right to left, then the vapor pressure of toluene decreases based on its mole fraction. And then the same thing, if you have pure benzene on the left-hand side, its vapor pressure will decrease as you add toluene. So you can add those two together and get the total vapor pressure above a solution where both components are volatile by adding together basically the individual pressures that you've calculated from Rayout's law for both components of the solution. Okay, I think I'm going to take a little break and then we'll come back and finish this. We're almost done, but you can have those things think in for a little while. Going to stop share.